So let's say they don't want you to get all the marks in the exam. So they ask you to find the nth derivative of h, the general derivative, the value of the derivative for any integer value of n. So the question is, how can we find the nth derivative of h? Well, the easiest thing to do is to find the first few derivatives, ideally the first four, and then we observe the pattern that is being formed, and then we use this observation in order to make a conclusion. So let's begin. The first thing we realize when giving this function a good look is that it's a product of two functions. Therefore, it makes sense for us to use the product rule in order to differentiate the function. So let's go ahead and find the first derivative. So according to the product rule, we take the first function, multiply it by the derivative of the second, and then we say plus. We take the second function and multiply it by the derivative of the first function, right? So now writing this derivative nicely, then it means the first derivative of h, it's just going to be x squared e to the x, and then we say 2x e to the x. Okay, fine. So now we move along and find the second derivative of h. So now we are simply going to come and differentiate this part, right? Okay, fine. So, well, if we look at the first part, well, it's still the same as the original function. So it stands to reason that the derivative of this part is just going to be exactly the part that you see here. In other words, it's just going to be this part itself. So we take it as it is and put it here. So we have x squared e to the x, and then we say plus 2x e to the x. But we are not done, right? Because by doing this, we were actually differentiating this function. So it is still necessary for us to differentiate the second function as well, or the second part of the first derivative. And of course, in order to do that, we use the product rule once again. So we take the first function, multiply it by the derivative of the second, take the second function, multiply it by the derivative of the first. Do you see that? And of course, right away, we can see that we actually have like terms, right? So these two terms are like terms. So we are simply going to add them up, and then we rewrite our derivative nicely as well. So it means our second derivative, nicely written, will be x squared e to the x. And of course, 2 plus 2 is 4. So this is what we have. And then we have 2e to the x. Okay, fine. So now we are ready to find the third derivative of h. And once again, we can see that, well, the derivative of this part, it's just going to be exactly this. So we don't bother ourselves. We just write it as it is. So it's x squared e to the x, and then we say 2x e to the x. Okay, fine. So now we come back and differentiate the second part of the second derivative, all right? And once again, we can see it's a product of two functions. So we use the product rule. And this is what the product rule is saying. And then we come back and find the derivative of the last part. Well, derivative of 2e to the x, it's just going to be 2e to the x. And once again, we realize immediately that these two are actually like terms, but they are not the only ones. These two are also like terms. So we are simply going to add them up and write the third derivative nicely. Well, we still have x squared e to the x, and 2 plus 4 is 6. And of course, we say, well, here we are just going to have 6 as well, e to the x. So now we go for the last one. Now we want to find the fourth derivative. Well, for some people, it's actually enough after finding the third derivative. Some people, they're able to see the pattern by just finding the first three derivatives. Well, I'm going to find the first four. Right. And of course, we already know the derivative of this one. Well, it's just going to be x squared e to the x plus 2x e to the x. Okay, fine. And then we move along and find the derivative of this one, right? And of course, using the product rule once again, we get 6x e to the x plus e to the x times 6. And then we'll say the derivative of the last one remains that. So now it's time to rewrite the fourth derivative nicely. Of course, by collecting the like terms, so we get 8x e to the x. And of course, 6 plus 6 is 12. So this is what we have. Okay, fine. So now we can make an observation in order to find the nth derivative of h. Well, this is the first thing we actually observe. And what is that? Well, here we can actually see that the first term of each derivative has x squared e to the x, right? Yeah, that's what we see. Okay, fine. So what does it mean? Well, it means quite simply that the nth derivative, the first term of the nth derivative, will also be x squared e to the x. So that's the first thing we observe. Now let's look at the second terms, because what we actually realize here is that each derivative has three terms, except for the first derivative, right? Well, it actually has a third term as well. And what is the value of that third term? Well, if it's not there, it's 0, right? And how are we going to write our 0 in order to write the first derivative nicely? Well, we are going to define our 0 as 0e to the x. Do you see that? It actually has three terms. So the last term is 0e to the x, and then the last term is 2e to the x, and so forth. So that's what I wanted you to realize. Each term of the derivative contains, hey, what am I saying? I want to say each derivative contains three terms. Sorry about that. Okay, fine. So we are done with the first term. So now it's time to go to the second terms, right? Okay, fine. So what do we observe? Well, we go to the first derivative, and this is what we have. We go to the second derivative, and this is what we have. To the third derivative, of course, and to the fourth derivative, Right. Now what we can see here is that all these second terms, all of them, they have xe to the x, right? All of them. Which means quite simply, for the nth derivative, the xe to the x will still be there as well. But now the challenge is, what is the coefficient of this xe to the x? Well, it's very easy. So this is how we establish the coefficient. On the first derivative, we have a 2. On the second derivative, we have a 4. On the third derivative, we have a 6. On the eighth derivative, we have, in fact, on the fourth derivative, we have an 8, which means on the nth derivative, we have 2n as the coefficient of xe to the x. Now the question is, how did we decide that it has to be 2n? Well, it's for a simple reason. It's derivative number 1, and yet the coefficient is 2. So it's 2 by 1, right? For this one, it's 2 by 2. For this one, it's 2 by 3. And then for this one, it's 2 by 4. Do you see that? So for the nth one, it's going to be 2 by n. That is where the 2n comes from. Okay, fine. So now what about the last term? Well, what is the relationship? We need to look at that. What is the pattern that is arising here? Because for the last term on the first derivative, we have 0e to the x. On the last term of the second derivative, we have 2e to the x. On the third derivative, 6. On the fourth derivative, 12. But the most important thing we realize is all of them, they have e to the x, right? All of them. It's just a matter of what is the coefficient of e to the x. So let's try to look at these numbers and put them side by side and see if there is a pattern that is being formed by these numbers. So here I'm just going to look at the coefficients of e to the x. And for this one, we have a 0, we have a 2, we have 6, and we have a 12 there, right? Now, what is the relationship between all these four numbers? Well, we don't have a factorial relationship. That's the first thing we can see. Okay, fine. Even though 2 is actually 2 factorial and 6 is actually 3 factorial, but 12 is not 4 factorial. And 0, well, 0 is just 0 factorial. I know, we don't really have a relationship here. Do you see that? In terms of the factorials. So we move. Do we have an exponential relationship? No, because we don't have a constant ratio. 2 divided by 0, it's just going to be undefined. And this one divided by 2, it's 3. And this one is going to be 2. So it's not exponential. It's also not arithmetic because we don't have a constant difference. However, the relationship that exists is actually quadratic, right? Because if you say 2 minus 0, you get a 2. Here you get a 4. And here you get a 6. Do you see that? And then you come back again. And you say, well, 4 minus 2 is just going to be a 2. And of course, here you get a 2 as well. So now you realize we have a constant second difference. Yeah, now you understand fully that we have a quadratic relationship. So all we just need to do is to find the general term that describes these four numbers, right? So we know that we are going to have 2a, and we set it equal to the second constant difference. which means the value of A is 1. Okay, fine. And then we also have 3A plus B, which is equal to the first term of the first difference, right? But of course, we understand the value of A is 1. So this means the value of B will be -1. Okay, fine. But we also understand that A plus B plus C, it's going to give us the first term of the quadratic pattern itself. And since we know that A is 1 and that B is -1, so we have 1 minus 1 plus C, which means C will be 0, right? Okay, fine. But what does it mean? Well, it means quite simply that the general term that describes 0, 2, 6, and 12, it's just going to be 1n squared, and then we say minus 1n. And this actually makes sense, because if you want to test the fourth term, for instance, then you can just say 4 squared is 16, minus 4, you get a 12. So it's the truth. So that's the relationship between the coefficients of e to the x. So in other words, you're simply going to come and say, well, here we have n squared minus n, and then you say this is multiplied by e to the x. And this will just be your nth derivative of h. And believe me, guys, if you said this in the exam, they're going to be so happy that they give you all the marks. Thank you so much for watching.